So up next, we have the chain rule. So I'm going to skip a little bit of this definition, but make sure you know these conditions and when you can use it. But for the most part, uh, they should apply for most problems. I don't think we'll ever throw a question at you where like, oh, the chain rule doesn't apply here because it doesn't satisfy this. Just, I think it's most useful to remember that if you have some composite function, f of g of x, then you have this identity. So what chain rule is basically saying is that if you take the derivative of a composite function, then we take the derivative of the outside, which is f of x, because it's containing g of x. We take the derivative of that, and we keep the inside intact. So g of x remains the same on the inside, but then afterwards, we multiply that whole thing by the derivative of the inside, which is our g prime of x, right? So using chain rule, we can actually make a more generalized power rule. So before we had the same identity, except we had x here. So let f of x be a differentiable function, and let n not equal 0 be an integer. Then the derivative of f of x to the n is equal to n times f of x to the n minus 1th power times f prime of x. So this is just an application of chain rule that's extending our use of the power rule, basically making it more useful for us. It's kind of the same thing applies when we're just doing normal power rule, right? So in this example, we can treat our outer function as x squared and our inner function as just x, right? So our composite h of x is equal to f of g of x, which is just going to give us x squared. So if we take this derivative, we have h prime of x is equal to f prime of g of x times f prime of x. That's our chain rule identity. So we have 2. We bring the 2 down in front from power rule, and we're subtracting the power here. G of x is conserved inside as x, and we multiply the derivative of x, which is just 1, which just gives us 2x. So it's kind of showing that the power rule, this generalized power rule really does cover all our bases, and it also does more. So if we have any other function f of x, we can also apply this to that. Now we have a couple of examples of chain rule, so let's take a look at that right now. Now we're going to be practicing a little bit of chain rule. So this was our first example for this part. We have h of x is equal to natural log of 3x squared plus x. So remember that this is a composite. So we have f of g of x is our general form for this. So that would make our f of x natural log of x, and our g of x would be 3x squared plus x. So our equation for chain rule is h prime of x is equal to f prime of g of x times g prime of x. So let's go ahead and plug in. So f prime of x, the derivative of natural log of x, is 1 over x, but instead of x, we're subbing in g of x. So this is going to be 1 over 3x squared plus x, right? And then all we have to do is multiply by the derivative of what was on the inside, or g of x. So the derivative of g of x is going to be, using power rule for the first part, we have 3x squared. This becomes 6x. And then we have plus x, which is just going to become plus 1. And that's it. This is our next example, and this is going to be a little tougher. It's going to kind of include everything we've done so far. So here we have h of x is equal to 1 over x times e to the 3x times sine of x. So again, you can do this in 2 different ways. The way I wrote it out, it looks like a product rule with like another product rule. So you're going to have to do like an embedded product rule. Kind of tough. I'd rather turn this into a product rule over a quotient. I think that's a little bit easier, but you can do it either way that you prefer. Okay. So in this case, our f of x, or our numerator here, is e to the 3x times sine x, and our denominator is g of x, which is equal to x. And I decided to break down f of x into 2 of its own functions that we can use for our product rule. So I'm calling it t of x is equal to e to the 3x, and L of x is equal to sine x. You don't have to write all this out every time, but I just wanted to kind of keep everything organized and show you how everything's going to break down. So again, we have our general form for the quotient rule. but we're going to sub in some things for our product rule that's going to be a part of this. So let's go ahead and just rewrite that. So we have g of x, we'll keep that the same. Here's what we're going to change though. We have f prime of x, because now we have to include our power rule. So I'm going to use these two functions, and we're going to write our own power rule inside of here. So remember we have, let me just look how I wrote this. Okay. T of x times L prime of x plus, remember we have to do the opposite now. So we'll have T prime of x plus L of x. So there's our power rule, and we're subbing that in for f prime of x. And then over here, this is going to remain the same, f of x times g prime of x. And g of x on the bottom squared. Let me clear this up, and then we can work on this problem some more. All right, so I squished everything up here so we can continue working underneath. So now we can just go ahead and plug everything in, and we'll have our answer. So g of x is just x. This is multiplied by what our product rule was. So t of x was e to the 3x times L prime of x. So L of x is sine of x. So the derivative of that is just cosine of x. Now we're adding. We're going to go ahead and add the second part, which is t prime of x. So the derivative of t of x, if we were to do our chain rule, we're going to end up with e to the 3x is the derivative of the outside, and the inside is just a 3x, so the derivative of 3x is just 3, and we multiply that out here. And then we're multiplying that by L of x. I'm noticing that there's a plus here. That's my bad. That should just be a multiplication. So L of x is just sine of x. Ooh, yes. Okay, this is getting a little cramped, but I'll continue writing down here. So we're subtracting f of x, which was e to the 3x times sine x. And that's times the derivative of g of x, which is just x. I'm just going to leave that off because it's just a 1. So multiplying by 1 is not going to change anything. And that's all over g of x squared, which is just x squared. Just simplifying everything real quick, we can go ahead and rewrite this. We notice that e to the 3x is in all parts of this, so we can go ahead and pull that out all together, and we can distribute this x to the inside to both of these. So I'm going to do that all in one step. So e to the 3x is on the outside times, so x goes here, so we have x cosine x plus 3x sine x minus sine x all by itself. And then we have this whole thing over x squared. And yep, that looks correct. This is our final answer. Lastly, I want to talk about explicit versus implicit functions real quick. So explicit functions are functions where y is by itself on one side of the equation, with everything else on the other side being in terms of x or some other dependent variable. So this is like y equals x squared minus 2x plus 1, or y equals sine of e to the x plus x cubed. We see that y is all by itself, and we have the identity that y equals whatever's on the other side, okay? So, but implicit functions are functions where y is no longer isolated on one side of the equation, and it's not given as a direct equality of something in terms of x. So here we have y to the 4th plus x cubed plus 17 equals 0, or something like y times e to the y minus natural log of x equals 4. So here we see y is kind of dispersed among everything else and is no longer just y on one side equals whatever's on the other, right? So far, we've only taken the derivative of explicit functions, and taking derivatives of implicit functions isn't all that different. All we have to do is treat any y we see as a function with an unknown derivative y prime. Then we rewrite this derivative in terms of that y prime. So for example, say, let's just take a look at this chunk right here. So y to the 4th, we use our generalized power rule, and we have f of x equals y would be here. So we would move the power out, so we have 4 times y, and this would become y cubed. But then what we'd have to do afterwards is multiply by the derivative of f, or in this case, this would be derivative of y. So you'd multiply that whole thing by y prime. It's possible to rewrite an implicit function as an explicit function and then take the derivative, but this tends to make our job a lot harder and can actually end up being impossible in some cases. So you could see here, like maybe you would want to, we could move this x cubed and 17, we could subtract them to the other side and then take the 4th root of that, of everything on this side, and then we'd have it in terms of y, but you'd have a case where you need to write a plus or minus on the outside, and you can't really do that. It's easier to just take the derivative first and then rewrite everything in terms of that y prime that you get. Okay, so I want to take a look at an example real quick, and then we'll be finished. So last but not least, our final example is about implicit differentiation and a little bit of tangent line thrown back in there. So we're given this function, x squared plus y squared is equal to 9. And we're asked to find y prime and then use this information to find the tangent line. Okay, so first off, we can just start differentiating. So 2x, we're going to differentiate the same way, just using power rule. But now for y squared, we're going to have to use our general power rule. So our f of x is our y. So we have to make sure that we do the outside. So we have the power rule like normal, 2 times y. And then we have to multiply by f prime of x, which in this case is just going to be y prime. And this is going to be equal to the derivative of 9. A constant is just going to be 0. Okay, and now we want everything in terms of just y prime. So y prime isolated by itself on one side. So let's go ahead and subtract 2x to the other side so that we're left with 2y times y prime is equal to minus 2x. And then we can just divide 2y, and we get minus 2x over 2y. And the point that we're asked to find the tangent line at, let me rewrite it right here. This is going to be, I believe, 2 square root 5? Yes. 2 square root 5. So we're going to find the tangent line here. So we can go ahead and just, first of all, solve what this slope is at this point. So we just plug in our x and y values. So x is 2, and our y is square root of 5. We can go ahead and cancel these 2's. We could have done that up here. But we get that y prime is going to be equal to negative 2 over square root of 5. All right. So now all that's left is to plug into our equation of the line, or our point slope form. So we have y is equal to m times x minus x1, or whatever point we're using, plus y1, whatever our y coordinate is. So plugging all that in, we have our slope is negative 2 over square root of 5 times x minus our point is 2, our x coordinate for that point, and our y coordinate for that point is square root of 5. So that gives us that our tangent line of this function x squared plus y squared equals 9 at the point 2 square root of 5 is equal to y equals negative 2 over square root of 5 times x minus 2 plus square root of 5. Okay? Please let me know if you have any questions. Tell me if I need to improve in any way. I want these videos to be the best they can possibly be. I want to be super helpful for you guys. Thanks for watching this far, if you got this far. Sign in below if you're taking this class spring 2020. And yeah, my email and my office hour information is down below as well in the description. Go ahead and leave a comment or email me or come to office hours if you have any questions or concerns. All right, I'll see you guys next week then. See ya.